Tuan is a PhD candidate in the School of Information Systems, SMU, and today he is going to talk to us about review generation. Let's welcome Tuan.
Okay, so hello everyone, I'm Tuan, and this work we published in the web conference this year. The topics that we are covering here is the review generation, towards the problem of building recommender systems. So without further motivation, because analysts have done it before, in this work we are focusing on the problem of building good recommender systems. And as mentioned, sparsity is a problem, and most of the time the interaction that we have between user and items is sparse. In this case, right, I just want to show some of the big companies where they actually heavily use the recommender systems in their business. And the more interactions that we have between user and items, the better we're going to know about the user preferences. And then the better we're going to recommend the more relevant recommendations to users. So one type of highly available kind of interactions in all user-based online websites are online reviews. So here, nowadays, online reviews are multimodal, in the sense that in addition to the ratings that the user given to the items, we also have text, review text. So user writes review review text to review items, and in addition to that, they also provide review images, thanks to smartphones. So nowadays, everyone has a smartphone. This kind of interaction is rich. We have a lot of information here, and inside the text actually review a lot of preferences of the user towards the items. So we want is to make use of this sort of information to know better the users, and then the objective is going to be estimate better the preferences and then give the more relevant recommendation to users. So in order to do that, we define a problem. So here, given a pair of user and items and an image, in this case, the image is optional. So we cover the case where the image is available or not. The output is that we want to estimate the rating score the user gives to the items. So that's going to be used for recommendation problem. Another task that we want to do is actually we want to mimic the user to write the review text. So let's say here's the user, here's the item. What should be the review text that this user going to write towards these items? And modeling these two tasks as a multitask learning problem, we hypothesize that these two are going to have each other. So from the review text, what we learn to write the reviews, actually we have to know the user better and the items characteristic to actually write the relevant text. And by doing that, we also learn the user preferences from the text and images. And then it's going to help us to predict the rating score more accurately, and then they're going to benefit each other. That's the hypothesis. In order to do so, we design a full neural network treatment to this problem. So the idea is that we want to design the end-to-end neural network. Then we can actually train the whole network with backpropagation without the multiple stage of pipeline. The model here might be a little bit complicated, but it's broken down into three components. The first component is the rating prediction component. The second component is the review text generation component. And the third one is actually the visual feature extraction component. So this one is optional, whether we have image or not. So I'm going to go through each of three components and talk a little bit more about that. I hope that some of you are familiar with neural nets, so then you can have a sense of what I'm trying to say here. So the first component is rating predictions, right? First, we have identity of the user and items. So we encode them using one-hot encoding. So each user and item will be represented by a vector, one-hot vector. And that actually helps us easily to map down the user and item into the low-dimensional space. That's what we call embedding space. So then each of the user and item is going to be represented as one vector in that space, what we call embeddings, user item embeddings. After doing so, we concatenate the two vectors, and we employ multi-layer perceptron, which is a basic type of neural network model to actually estimate the rating that the user gonna give to the item. So by only doing this one, we can already give recommendations, right? Because we have a score, then you can actually rank the items and then you can make recommendations. But it's not enough because here we want to make use the review information to actually enrich the embeddings, user item embeddings here to know the item and the user better. So then in the end we want to estimate the score more accurately. So we come to the second component where we make use of the text data. In this case, we're gonna use a recurrent neural net, which is a type of neural network naturally designed for temporal sequential data and like text data. It's naturally designed. So this kind of network actually has the ability to generate the data, the text data. So here we use LSTM variant of the recurrent neural net. And the input of the recurrent neural net here is the embeddings of the user and item. So what we hope is that we input the embeddings, user item embeddings at the input of the net. So then during the training, the information, the supervised information from text data actually backpropagate to the embeddings. So actually the embedding of the user and item going to capture more information from the text data. So that's the idea of this review text generation process. At this point of time, the review generator take the input, also input from the rating prediction as a feature. So here the rating prediction component gonna output some features, and that feature actually give the sentiment signal to the review text. So what kind of text are we gonna write here? Is it gonna be positive text or negative text? In the scenario where we have additional image, so we're gonna use CNN, convolutional neural net, to. The idea here is that we're gonna compress image into low-dimensional feature vector to be given as input to the review generation process. This is another source of information. So we want, in this case, we want the text more relevant to the content inside the image. So it's not some general text between the user and item, but it actually describes something that user want to say inside the image. Yeah.
I'm actually curious, how do you get the annotation from the image?
How do I get annotation? Annotation here is another way to call the different filters. So actually CNNs, there are multiple filters. So this is one of the layers inside CNNs, and you actually feed the image through multiple layers, and then you, at some layer, you will have multiple filters. So the hypothesis is that each of the filters going to represent one semantic meaning of the image. So each one is actually a filter, and you vectorize it. So it's spatial matrix, but then you vectorize it, and then you return to the what we call annotations.
I thought annotation something like food or like a soup noodle or something like text. It's not text.
It's convolutional neural networks.
I see.
Yeah, it's another type of neural networks that work with spatial data, and image is one type of spatial data. Yeah, but think of it as if you're not familiar, think of it as just an encoder. It's a compressor. It's compressed image into lower dimensions form of feature vectors. So we want to input the information into the review generation process. So here we have two types of information that have actually input to the review generation process, which is sentiment features that come from the rating prediction component, and the visual feature actually come from the image. So we observe that when we generate the text, right, the LSTM generates word by word, and the keywords inside, the important words inside the text. Most of the time we observe that either is a sentiment word, or some word that actually describe the content inside the image. So we require the model to actually, you have to do a trade-off. You have to either condition on the visual information or the sentiment information when you actually generate this word. And we modify the LSTM cell a little bit. What we call here is a fusion gate. It's a mechanism actually to do a trade-off between the information. You want to flow this much of information of the sentiment to this word, or this much of information to the visual, this much of information of visual to this word. So we ask the model to do a trade-off. Another way to think of it is actually this design is a regularization mechanism to the generation process. So that's why we have our LSTM cell, where we plug into the recurrent neural net. So again, here is the overall architecture where we actually have a complete picture of the model, 3 components. After design the model, we want to answer 3 questions. So the first question, of course, we care about the performance of the recommendations. So we want to see how well the model can actually perform with the task of rating prediction. Another task that we care about is actually the quality of the text. We also want the quality of the text to be good. And we want to compare the text that the model generates with the real review to see how close is that. Another question we want to answer is that if we actually remove the components of the models, because we have different scenarios. Sometimes we don't have image. Sometimes we don't have text, for example, and we have only the rating. So if we don't have, if we are in that scenario, so how each component actually contribute to the performance of the model. To answer those research questions, we conduct experiments. So first we collect data from Yelp.com, which is one of the famous food recommendation and reviews website. We draw the data from 4 cities, Chicago, Los Angeles, New York, and San Francisco. The data set is quite big. Thanks to Venom, we use Venom to draw the data. So we have 2 tasks to care about here. First is the rating prediction, and again is the review text generation. And for each of the tasks, we have 2 corresponding metrics to measure the performance of the model. And each of the tasks, we're going to have corresponding baseline, a previous model, to see, to compare with those previous baselines to see actually our model actually can perform better than those baselines or not. To answer the first question, we compare with 2 groups of baselines. The first group of baseline, what we normally call collaborative filtering baselines, where they only use the rating information. They try to predict the ratings without using the other source of information. The second group of baselines, they actually make use of a review text. And we can see between the 2 groups, our model, the red line, the MRG, actually outperform the baselines. In the case where we actually reduce the number of training data, so we actually specify the data. We use 80% of the training data here, and then we actually reduce the size of the training data to 20%. So we use the other 80% to do the testing. And when the data becomes sparse, that's when actually the additional information from the text help the model to actually make a more accurate information. Because we don't have a lot of ratings information to learn from, then you need to make use of the other information. The second question that we want to answer is how close our generated text compared to the ground truth review text. And here we compare with 2 baselines. The first baseline, they generate the review text based on the user item and the rating information that they predict. The second baseline is actually image captioning problem baselines, where they actually generate text based on the content of the image without knowing who are the user items and the rating scores. And from the results that we experiment on our data set, actually we see our model actually can leverage 2 sources of information efficiently, and they actually generate the text much better than the other 2 baselines. For the third comparison, where we actually see the contribution of different components inside our model. So the first chart, we show the performance of rating predictions. And as you can see, right here, the first column is the performance of the model, the multi-level perceptron, where we don't have any other information. We only predict the rating based on the user and items. And when we actually input the text, so it's the second column here, and we can actually see the improvement, the significant improvement. So this is the IMSE score, which is lower is better. And we see the significant reduce of the IMSE in this case. But when we actually input the photo, it doesn't have much, because the photo actually just to make the text more relevant. And actually doesn't have much in terms of the preference learning to actually have to predict the rating better. In this chart, we show the performance of the quality of the text that generated. And we can see when we actually input the rating, which is the sentiment signal, then the text is more relevant. And when we input the image, it's even improved higher, because the text now is more relevant to the image. Here we show one case study that after we train the model, so then we come back to the test data, and we try to generate some text, infer the rating score, and see how the model actually learns from the data. And in this case, we text the similar photo from the same restaurant. So actually, this one is the same item in the sense that two different users actually reviewing the same item, the same dish in this restaurant. And we see this is the ground truth rating. So this user actually give positive rating, 5. This user give the rating 3. We say it's neutral, but actually most of the time the rating 3 tend to be negative. And here are the texts that they given to the dish. And here the bold texts are the texts that the model generates. And in this case, the model actually know what is what is the image is about. So it's about a clam chowder, and they generate a text about clam chowder, and they have the sentiment signal from the rating. So then they know this should be a positive text. So then they write the clam chowder was good. In this case, they say the clam chowder was a little bit too salty to express the sentiment. And actually in the ground truth data, actually the real user also say that this is salty. Here comes the conclusions. MRG model is a neural network model for multimodal review generation. And this deal with the two tasks. The first task is rating prediction. The second task is review text generation. And we conclude that the preferences are captured in the process of constructing multimodal review, and actually it helps for recommendations. For potential application, this model, of course, is going to be used for recommended system, but with some explanation. So you actually recommend this user, right? But with the review text, it's kind of like show you some explanation why I recommend this to you, because this might be possible reviews that you give to this item. And another application could be personalized image captioning, where this model you learn the preferences of the user, and you actually can write the text that is relevant to the image. So in a scenario where you use Facebook or Instagram, you post photo, so those systems can actually kind of know your preferences and give you some short caption to the photo that you upload. Yeah, and the model we publish the code here, so you can go and check it out. All right, thank you.